All right, guys, let's take a look at our next problem. Okay, so it's asking us for the circuit shown below, determine the node voltages VA and VB. So they're asking us to find the voltage in the circuit over here and over there. So before we tackle this problem, first of all, between the two strategies that we have in time domain analysis, KVL and KCL, understand that KCL, or Kirchhoff's current law, or nodal analysis, is definitely the move over here because they allow us to solve for voltages quickly. And once we have those voltages, really, we can answer any other part of this circuit, any other part of this question may have. We can find the currents, the power, the voltages everywhere. So before continuing on this problem, let's go over the notes on nodal analysis a little bit. So when it comes to KCL, guys, remember the steps that we've gone over. It's a quick 4-step process. The very first step is to pick a ground somewhere if it is not given to you. Now that step is done for us over here. We have ground right there given to us as a reference node. The second step is going to be to write constraint equations for every voltage source present in your problem. So in our case over here, we see a voltage source right there. We need to write down a constraint for it and understand that this source is going to maintain a 12-volt difference between its negative and positive terminals. So essentially what we're saying here is that VB minus VA must be equal to 12. So VB will be 12 volts higher than whatever VA may be. Next, you're going to write nodal equations for every significant node. And what that means is a node that's significant, in other words, is a node that you do not know the voltage at. For instance, this bottom node here would not be a significant node because we know it's our reference, it's equal to 0. But every other node, I don't know the voltage here, I don't know the voltage there. That's definitely, those nodes are definitely significant, and we're going to write nodal equations for them. And we're going to do this in a way such that the current, whenever we have a choice, the current is going to be exiting the node. So when you're exiting, you are positive. If you're entering, you're negative. But we are always going to choose exiting unless, of course, we're forced by some source. At this stage, you should realize that it's a good idea to create a supernode if there's a voltage source between two significant nodes. Now, even though this sounds like an intimidating thing, a supernode actually, the technique actually exists to make your life easier. And so we're going to solve this problem. We realize here that there's a voltage source between two nodes whose voltages are both unknown. And so we're going to solve this problem using a supernode. But first, I will do it, or at least set it up, without using that supernode. And you will see how much simpler the problem becomes once we apply this method. And lastly, we're going to solve, once we have these equations, we should have enough equations that allow us to solve for all of our unknowns, and we'll be in a position to answer whatever is being asked. Before we continue, guys, I want you guys to be absolutely clear about something. When you are calculating or trying to calculate the current at any given moment, any given node, let's say node A, you can encounter really one of three things. There's either going to be a current source, or a resistor, or a voltage source. That's it. Those are the three possibilities. And you should understand how to write out the expression for each one of those three scenarios. If you are given a current source, and you want to write out its expression in your nodal equation, understand nodal stands for KCL, Kirchhoff's current law. You're adding up currents. Now, if you're adding up currents and they're giving you the current, I mean, there's not much to do. You use the value straight up. Next, you can have a voltage source. Now, the problem here becomes you never know the current going through a voltage source. And therefore, you have no choice but to assign a variable to it. And so that is what you're going to do if you're trying to figure out what the current through this source is. Well, you're going to say it's I source. But you should know in advance, though, that a current always leaves the positive terminal of a voltage source and enters the -1, as long as it's a source. So the direction of these guys, cannot be tampered with. They dictate the direction. The current here is for sure flowing that way. The current here is for sure flowing that way. And if you have a resistor, to calculate the current passing through a resistor, you're essentially going to use Ohm's law. Current is V over R, or the change in voltage, the voltage drop divided by the resistance, VA minus VB over R. And remember, over here, you'll always take the direction as exiting your node. If you understand these things over here, this problem should be fairly straightforward to solve. And remember, we're going to do this two ways. The very first thing I'm going to do is I'm going to solve this problem as if we didn't know anything about supernodes. And then I'll introduce you guys to the concept of the supernode next. So one of the things I like to do, guys, and one of the things that will really help you guys out, is to spend the time highlighting your nodes. And we're going to do this in every one of our problems. Understand that a node is nothing more than a piece of wire. A lot of you guys get confused with this concept. You think that when I say node A, I mean specifically that point. No, node A, guys, is this entire piece of wire. Similarly, node B would be this piece of wire. And then our last node, or node C, would be the bottom piece of wire, and that is going to be equal to 0. So we have 3 nodes in this problem. We can create this circuit using 3 wires. And we know over here, if I call this A and this B, and let's call this C, VC, of course, is equal to 0. It's our reference. Step number 1 is to write a constraint equation for every voltage source. So we know that VB minus VA must equal to 12. And now you're going to start writing nodal equations for each node. So let's do them over here. If I take a look at node A, I'll have 3, and node A is connected to 1 and 2 and 3 branches, so 3 terms in my equation. I can see that this current is coming in, so if it's coming in, I don't like that. It's a negative term, negative 1.5. I'm going to use the value straight up, of course, it's a current source. To figure out the current over here, it's going to be VA minus VC, which is 0, divided by 6. And to find the current over here, we know it's going that way due to the polarity here. And I never know the current in a voltage source, and therefore I'm going to assign a variable plus IS, and that is going to equal to 0. Similarly, we're going to do node B. At node B, once again, there are 3 branches over here. Starting over here, we see that this current is entering the node, so negative. It's a voltage source, so I do not know the current passing through that source. I'm going to label it IS. The next current is going down out of the node, so positive 3.5. And then finally, VB minus VC divided by 3, or VB minus 0 divided by 3 equals 0. And so that is it, guys. That's the analysis over here. Take a look at how many unknowns we have. We don't know VA and IS and VB. There are 3 unknowns to this problem. And if you count the number of equations we have, 1, 2, and 3, so it's a 3-equation, 3 unknown problem. You can quickly solve for VB or VA over here. We understand that VB is 12 plus VA. Plug this in both everywhere you see VB, and then you'll have a 2-equation, 2 unknown problem. It's manageable, but it turns out that there is a smarter, faster, quicker way of solving this. You guys should try this at home and see if you get the same answers that I am about to get with the concept of the supernode. So let's take a look at that. I'm going to put these equations away for now. So these are the 3 equations we kind of had. So now what the supernode does is that it is going to engulf the voltage source that causes problems. In this particular case, this guy is causing a problem because it is creating an additional variable IS, as we saw. So what we're going to do is we're going to kind of merge these two nodes together, thereby creating our supernode. So we're simply going to pretend that this guy is not there, and all of this is one big node. The one thing we are going to maintain, though, is that the relationship between VA and VB. If I'm going to call this side of my node, the side to the left of the voltage source, VA. And we know from this equation that VB, this side, is nothing more than VA plus 12. And if we just write this node like that, using the relationship between VA and VB on either side, we know VB is 12 more than that, and I'm stating that. Then we can get the job done. Instead of having 3 equations and 3 unknowns, guys, watch what will happen. We'll have one equation and we'll get VA and VB just like that. So our equation is going to be what? We have 1, 2, 3, and 4 branches in our supernode. Whoops. So let's do the work over here. So our first branch has a current coming in, so negative 1.5. Our second branch is VA minus 0 over 6, so just VA divided by 6. Next one has a current going out, so positive 3.5. And then finally VA plus 12 minus 0 divided by 3, so VA plus 12 minus 0 divided by 3 equal to 0. It's as simple as that. So in order to solve this problem, we're going to start by, let's say, multiplying everything out by 6. So let's start by multiplying each one of our terms by 6. That'll simplify things. I'm also going to take these constants to the other side. If I multiply this by 6, I get VA. Multiplying this term by 6 is going to give me another 2VA plus 24. 3.5 minus 1.5 is 2. And 2 multiplied by 6